Welcome. My name is Martin Hoenigl. I'm Associate Professor at the Division of Infectious Diseases and Global Public Health at UCSD, and I will talk now about matched pairs and groups randomization as one option for a complex trial design. So matched pair or groups randomization means that you have matched pairs or groups here in the same color, A and B, or C and D, and E and F, and they get all randomized within the pairs to intervention 1 and intervention 2, or standard of care. So what you can make sure is that you basically address some potential confounders by randomizing matched pairs. So A and B are similar, for example, for your confounders, and you make sure one is going in one arm of the study, the other one is going in the other arm. And the same with C and D. So after initial screening, patients are matched into pairs, and within each pair, one participant is randomized to intervention 1, and the other participant is randomized into intervention 2. What are the advantages of such a matched pair design? It really reduces the bias between the arms by matching covariates such as age or disease severity in pairs or groups of patients who are each randomly assigned to one of the two interventions. Example here, and this is basically going beyond just pairs but really going to clusters and larger designs, is this example here with 3 clinics assigned to showing of informational videos in waiting areas to promote colonoscopy screening versus 3 controls with regular TV programming. You can imagine in such an example basically you want to make sure that the clinics are comparable between each other, and that's why such a matched pair, matched group design would be an appropriate fit here. There are a number of advantages, and we can start really kind of like with the most simple example for a matched pair. And this is basically matched organ or within an individual by comparing an intervention on symmetrical parts of the body, such as arms, eyes, feet, kidneys, or the skin. Here, basically, we must make sure that each site must start in similar state, well, normal or similar diseased, and the intervention must really remain localized basically to one organ. So we have to make sure that the intervention is not crossing over, for example, from one kidney to the other kidney. One example, and one simple example, is of course 2 sunscreens that are each applied to half of the body to prevent sunburn. Here we would make sure that both sides of the body are equally tanned, both arms are equally tanned, and then we can apply these sunscreens. Another option is if you want to test mosquito repellents, for example, do different and compare them. We can have basically how this is tested is that you put your arm into a cage full of hungry mosquitoes after applying the repellent. And basically you could at the same time have your 2 arms put into 2 cages with 2 different repellents on it, and afterwards you count how often basically you have bites on both arms. When we go beyond the matched pairs to really groups or cluster randomization, there's a number of important key elements. First of all, it's important that really here it's not pairs basically, but it's group or clusters of participants, like the clinics that are assigned to an intervention. So the whole one clinic is receiving one intervention, and another clinic that is matched is receiving the other intervention. Typically, randomization is done in matched pairs, but it's not individuals, but really, these big clusters or groups that we are matching. Of course, it's important to consider that this is less efficient statistically than randomizing by an individual, because with such a cluster, a big group, we also potentially introduce more confounders as well. And it's really often used to assess public health programs, such as educational or dietary interventions. It may enhance subject compliance through peer pressure. This is also important to consider. It's a key element that could be an advantage, but then it also could affect basically validity of our findings because it may not be translated that well into real life to an individual level. So advantages here is that it really avoids leakage of an intervention to controls within groups, because we have two separate clinics that are geographically in different places. So there's much less leakage of the intervention between the two groups. And it allows also for efficient application of interventions to groups. Examples for such a group and a cluster randomization in matched pairs is education to reduce tobacco use in baseball players or behavioral interventions to reduce HIV transmission by HIV-infected clinic patients. So for the baseball players, the groups or clusters would be baseball teams, right? And for HIV transmission, it would potentially be HIV clinics, different HIV clinics in different settings that are matched and then assigned to intervention 1 or 2. With cluster design and matched pair design, there's a number of important disadvantages, of course. It starts off with a greater complexity in design and analysis. We also need to account for non-independence, and that's what I said before, this cluster effect. There might be the peer pressure, there might be within a cluster, so people might be more adherent than they would be if the peer pressure and the whole cluster effect was not there. It also requires a larger sample size to achieve statistical power, although of course it's much easier to get a large sample size once you randomize a whole baseball team, for example, a whole clinic. And the larger and fewer the number of clusters, the greater is the loss of statistical power for the same number of patients. So you want to make sure you have a good number of different clusters when you do such a study. This brings us to our exercise. So the objectives here are, during watching the lecture, I'll give you two options, and please select for yourself the research question that may be best answered with a cluster randomized trial design. After watching the lecture, then you can design the randomized clinical trial with the assigned cluster randomized trial design, including a flow diagram, define the primary outcome, and list really for both options benefits and disadvantages of the cluster randomized trial design versus a standard parallel design. So here comes the exercise. Option 1 is to evaluate the effectiveness of 2 months of semi-weekly individual aerobic exercises versus sleep deprivation to reduce levels of self-reported depression in elderly patients with chronic to moderate depression. Option 2 is to evaluate 2 regimens of stretching and warm-up to reduce joint injuries in professional baseball players during preseason training. Give you a few moments to consider your choice. Come to the solution. So really option 2 is the best example for a cluster randomized trial design to evaluate 2 regimens of stretching and warm-up to reduce joint injuries in professional baseball players during preseason training. The different teams, they are fairly matched, of course, because the same positions, etc. So they they would basically be used as clusters. So different baseball teams would use as clusters. Option 1 is less good basically as an option because of course you can think about sleep deprivation in a whole and the cluster effect that may really kind of like be a big problem there for option 1. What's important of course also for option 2, that we need to account for non-independence. We need to account for the cluster effect, right? So it's not necessarily we are not necessarily able to translate this to an individual level. Because of course in a team, in a baseball team, everybody will be doing basically the assigned exercises, and the cluster effect will in addition benefit that. And the larger the fewer the clusters, the greater is the loss in statistical power. This is also an argument why option 2 is better, because we can have numerous baseball teams in the league basically. For option 1 it may be a little bit more difficult to refine multiple comparable matched clusters, because there might be multiple influences that may make these basically depressed patients self-reported. Let me restart. While for option 1, this may also be a problem in terms of many clusters, right? I mean, a typical selection, if we would choose option 1 for the cluster randomized trial design, it would be basically elderly homes, for example. And when you think about elderly homes, of course, there are multiple confounders that come in there. They are not as well matched as, for example, professional baseball teams. So that could be a problem also finding with matching. And then, we could also, we would have to enroll a ton of different elderly homes that in part all get sleep derived. So this would really not be feasible on a large scale. Thank you.